All right, welcome back. Let's take a look at some more examples using the method of substitution. So here we go. The first of three examples, we have this integral here, and we notice that there's a logarithm, a natural logarithm. Much like in the previous video, a good idea was to let the quantity in the bracket become the quantity that we're going to substitute for. So in this case, we can let u equal the natural logarithm of x. So there you go. Now, what is the derivative? Let's get that differential form going. We have here the derivative of ln x, which is 1 over x. And there's your differential dx. Okay, now let's see if we can substitute all this information and turn all of these x's into u's. Well, looking at the numerator, we have a very safe situation there. We have u to the 4. The only situation now to deal with is the quantity here, x, and the dx. Well, if you look carefully here, we do have that as well over here, dx over x. What we can do is take the dx over x here and replace it with du. So I'm going to do that exactly as such. I'm going to take that dx over x, and I'm going to just call it du. Well, what about the 3? Well, the 3 just stays still. Nothing happens there. It's kind of boring. Okay, now we're off to doing a power rule. We have u to the 4, whose antiderivative is u to the 5 over 5. Don't forget that we have a factor here of 1/3 that we can just take out. And of course, our constant of integration. One final step, let's just substitute back in what u is. U is actually ln x. And in the denominator, we have 3 by 5, or 15, plus c. So there you have it. In this next example, we have some radicals involved. So how are we going to approach this? Well, what you can do is let u equal the quantity here. Now, how do you know to do that in advance? It's more of an experience thing, I guess. I mentioned it several times in my derivatives videos. You can find that playlist also. In this case, I recall that if we let u or some quantity equal root x, the derivative of that is 1 over 2 by root x. So this is more of an experience that we recognize the derivative of root x. Well, what about the plus 1? No problem. Adding a 1 here doesn't change much. We still have the same derivative because the derivative of 1 is 0. And don't forget, this is a differential form, so I will write a dx there. Now, let's start comparing. Okay, so we have here this quantity here. Well, that's just u. So let me just circle that this time. So as we do them, it's kind of like a checklist here. We have here 3 over u. Trying to get a straight line there. Much better. Okay, now what about this dx and the x here? We have dx divided by x. Well, we have that as well here. See, dx divided by x. In fact, what I will do is just quickly write this as 2 du. So there you have it. Dx over x is equal to 2 du. And you can see now that we have a quantity here which involves u. Okay, so it's just a matter of taking the 3 and the 2, turning it into a 6, and recognizing that the antiderivative of 1 over u is the natural logarithm of u. And finally, we can replace the u with the square root of x plus 1. So here we go. Ln of root x plus 1 plus c. One last thing to mention here, the absolute value of a positive quantity is going to remain positive. And as you can see here, this root x is non-negative. That is, it's 0 or greater. Well, when you take a quantity of 0 or greater and add 1 to it, it's definitely positive. So I'm just going to take away the absolute value and put an ordinary bracket. Moving on to this last example, we have this idea of recycling. I mentioned recycling in an earlier video. If we let u equal the quantity in the brackets, x cubed minus 1, the differential form gives us the following. Well, that derivative is 3x squared. Don't forget the dx there. And when you compare this to the original question, it kind of looks good, but it kind of doesn't. The issue is this. Don't you wish that was x to the 2? Because then it's x squared dx. Well, that's okay. No problem. What you're going to do here is replace the x to the 5 with x to the 3, and then x squared. and then write down the rest of the integrand. Well, x cubed minus 1, all cubed, dx. And now we can organize things a bit better. So this stuff here that I'm underlining is u to the 3. The x squared and the dx together, well, that's right there. I'll just move the 3 underneath. So that's going to be du over 3. And finally, well, what do you do with this x cubed? No problem. Take a look at the original question here, and you see that we can what I call recycle. In other words, we can take this x cubed and isolate for it and have u plus 1. So there you go. Let's put u plus 1 there. So after a little bit of bookkeeping, which is all this really amounts to is bookkeeping, we have what we need to answer the question. Okay, so what I'm going to do now is just expand this out. I could take the 1/3 out of the integral and have your u to the 4 plus u to the 3 du. Now, let's get those antiderivatives. So that's going to be u to the 5 over 5 plus u to the 4 over 4. And don't forget your constant of integration. One last step to clean it up. But first, I'm just going to shrink things down. I want to get that final answer on one slide. So here we go. There we go there. So let's take this last step now and deal with it. We have here, I'll distribute the 1/3 as well. So 3 times 5 is 15. So we have 1 over 15. And then we have here 3 times 4. So that's 1 over 12. And what about the u's? Well, recall from the original substitution that u is equal to x to the 3 minus 1. So that's x to the 3 minus 1 there, and x to the 3 minus 1 there. There you have it. Hopefully that made sense, and we can move along.